Hello everyone, today we're talking about some important subspaces. So this is material from 4.2. So we've been talking about this abstract notion of subspaces of a vector space, and today we'll kind of bring it back down to earth a bit and talk about how these relate to matrices that we've been studying. And so let me just maybe give you the top-down idea here. If A is an m by n matrix, then kind of A comes with two subspaces. So a subspace, first of all, of Rn called, what's going to be called the null space of A. And then it's also going to come with a subspace of Rm called the column space of A. Okay, so if I draw kind of my usual cartoon here of thinking about a matrix A, it eats vectors in Rn, right, and spits them out in Rm. So here's A times x. Then my null space will be, some subspace of Rn here. The column space will be a subspace of Rm. So just to kind of put everything in a kind of abstract picture here, this is where things live. And so we'll define these now. The null space, it turns out both of these actually are going to be things we've already studied in other contexts. So let me just recall that if A is m by n, we can consider the system or the equation ax equals 0, which we call the homogeneous system. And we spent some time with that. How do you actually describe the solution set, right? It's in terms of reduce your matrix to a reduced echelon form, et cetera, et cetera. And that's actually our first definition. So if A is an m by n matrix, then the what's called the null space of A is the set of all solutions. Let's say the set of all solutions to that homogeneous. Okay? And in a more kind of maybe fancy math way to write this is it's the set of x in Rn, right? We know that every solution will have n entries such that Ax equals 0. Okay, so in pictures, the null space, if I go back to my picture up here, everything that's in the null space, whatever the null space is, it'll all get sent to 0. So all the stuff in the null space gets sent to this vector 0. All these vectors, it's exactly the stuff that gets sent to 0 under this transformation A. Okay, so again, the good news is that this is something we've already studied. Let me do this. Let me consider an example. So if I take this matrix A, right, so this is a 2 by 3 matrix. I want to know, let me ask you the first question. So, I should first point out that the null space of A is going to be a subset of, there's 3 variables here. So all solutions to the homogeneous will have 3 entries, right? Every solution will have 3 numbers associated to it. And let me ask you a question. Is U, the vector U, 5, 3, minus 2, is this in the null space of A? Okay? And what I claim is that, so this is the usual story of our favorite man on the street who gives you a vector and asks, is this in the null space of your matrix? This is easy to check, right? All you have to do is, let's say, just do the calculation. It takes some work, but we'll see that it's pretty straightforward. All I have to do is say, what is A times U, right? I want to know, is this a solution to the homogeneous, Ax equals 0? So what I'll do is I'll consider A times 0, which in this case is A times U, which is 5, 3, minus 2. And of course, this will have 2 entries. The first entry is going to be what? Let's see, 5 minus 9 plus 4, which indeed is 0. And then the second entry will be minus 25 plus 27 minus 2. Yep, it's 0. I get the 0 vector, so indeed, this implies that U is in the null space of A. Okay, so easy to check. If you've got a if you give me a vector, it's easy to check if it's in the null space. Okay, so maybe the first important fact here that, ties it into the subspace theory is that if A is any m by n matrix, then the null space is a subspace, not just any old subset, but it's a subspace of Rn. Now remember what that means. I'm not going to go into the details here, but what this means is that it contains the zero vector and it's closed under vector addition and scaling, right? You guys know now that a subspace is defined by having the zero vector and having this property. If you take any two vectors in that thing and you add them, it stays in the thing, and if you scale one of the vectors in the thing, it stays there. I'm going to talk about one way to prove this, I think, in our discussion, but if you think about this, also follows from the fact that, well, the solution set to the homogeneous is always given by, right, the span of a bunch of vectors. So if you remember, I'll do this in a second actually, but if you remember, when we were talking about solving the homogeneous systems, the way to do that is you row reduce this thing, and then in the end what you're getting is the span of a bunch of vectors, v1 through, let's say, vp, where you have one for each free variable. Okay, so I'll do an example of this, but this should be familiar that when you were solving homogeneous systems, it was always span of a bunch of vectors, and we know that span is always giving you a subspace. We talked about that last time. Okay, so actually let me kind of do that example. So for example, let me do this same, so let's do the A as above. So if I want to describe the null space, to describe the null space, null A, we, solve AX equals 0. When I say solve, I mean, look for the solution set. So I'm going to put in this, kind of secret 0, 0 as usual. I don't really care about that because when I row reduce, this thing will always stay 0 on the right-hand side. But let me go, do my row reduction. I'm going to leave out the 0, 0. This will be 0, minus 6, looks like minus 9. Maybe I'll now scale that last row by minus the sixth. So this will be 0, 1, 3 halves. And now I'll clear above this pivot. So this gives me, see if I can fit it here. So 0, 1, 3 halves. And then this will be 1, 0. I'm taking 3 times this. So this is 9 halves. 9 halves times 9 halves minus 4 halves, so that's 5 halves. And so what you get is, hang on, did I do this right? I had something different in my notes, but no, this looks right. Okay, so now what you get for the solution is that x has 3 variables, of course, and x3 is free. What we're getting is that x1 is minus 5 halves x3, x2 is minus 3 halves x3. So if I factor this out, it'll be minus 5 halves minus 3 halves 1. And so this is what I mean, is that you get the solution set is the span of, in this case, just one vector. Okay? So I can say this is the span of just the single vector minus 5 halves minus 3 halves 1. Okay? Okay, so that's the null space. Let me switch gears here, give you the other definition. So our other main definition of the day. Again, let me take an m by n matrix. Its column space is given by, well, the span of its columns, span of the columns of A. Okay, so not such an inventive name, but the column space, it's easy to remember. It's the span of the columns of A. So if I want to write this as a more kind of mathematical version, this will be span, the column space of A, which we write COLA. This will be the span of A1, A2 through AN. There's n columns. As usual, this is the These are the columns of A. So of course, as you know, the span of a bunch of columns is really all vectors that you can get as linear combinations. So x1a1 plus x2a2, xn an. Okay? And now a couple facts I want to just write down here. So the first fact is that, well, what we get immediately is that since the column space is defined by the span, then the column space of A is not just any old subset of Rm, but it's a subspace of Rm. And again, this is because it's defined as the span, and we always know that the span of a bunch of vectors is a subspace. And the other fact I want to write down, just so we have it, this observation, is that a vector, let's say B, is in the column space of A if and only if, right? If and only if it's in the span of the columns of A, which means if and only if AX equals B has a solution or is consistent, right? And so this will be important going forward. This is how you check if a given vector is in the column space. I think I'll do an example next time. I want to end with just maybe one, well, let's do that example that our running example. So if A was this matrix that we've been working with, then by definition, the column space of A is the span of, well, the columns, 1 minus 5, minus 3, 9. Okay, and so you can actually kind of draw this, right? So the span is all linear combinations of, let's say, 1 minus 5 is like that. Minus 3, 9 is, I guess, kind of like that. And then minus 2, 1 is maybe over here, or more like that, I guess, right? So you got these three vectors in the, don't look at that one, three vectors in the plane. The span is the column space. Now notice in this case, right, we can actually say something about the span immediately if I row reduce this guy as usual. So we already did this, but do this again. If I take, clear below that pivot, what was this? So this is 5 minus 6 and then minus 9. I see that there's two pivots here. And so what this means is that the span of these vectors is actually all of R2, right? Remember, if you have a pivot in every row, then the span of the columns is all of R whatever. There's two rows here, so it's R2. And so this tells me that the column space of A is actually R2, okay? In fact, what I can observe here is that the column space of A equals Rm if and only if A has a pivot in every row. It's kind of a general thing to notice here. Okay, so that's kind of introduction to null space, column space. We'll continue next time with more discussion, more examples. We'll see you then.